This video is going to talk a little bit about solving exponential equations in different scenarios that you may see and how to handle those different scenarios. So first I'm going to talk about a situation where you can rewrite your exponential expressions with the same base so that you can then just ignore the bases. So here's an example of an equation, an exponential equation, that we could solve by rewriting these two expressions with the same base. Obviously, I can rewrite 4 and I can rewrite 8 with the same base of 2. So I would write 4 as 2 squared and then tack on what was already there, the 2x minus 3. And I could rewrite 8 as 2 cubed and tack on what was already there, x minus 6. And once you have these expressions written with the same base, you can just ignore the base. 2 to the anything is equal to 2 to this other thing. We can just ignore those 2's. So we just have 4x minus 6 equals 3x minus 18. And at this point, this is like an Algebra 1 problem. Put the x's together on one side, so you subtract the 3x to get 1x, add the 6 to the other side, and you get negative 12. And you don't need to check and see if this is extraneous because this is an exponential equation. The only time you need to be concerned about exponential equations or about equations having extraneous solutions is when you're solving a log equation. So what if we had a scenario like this? This is very similar to the first problem, except I changed the 8 to a 9. We don't have the opportunity to rewrite these with the same base anymore, so you need to take a different approach to solve this exponential equation. So notice that the x's are in the exponent right now, and in order to get them out of the exponent, we can take the log of both sides. Now, it doesn't matter what kind of log you take. You can take the natural log, you can take the log, you can do log base 4, you can do log base 9. It probably wouldn't make sense to do log with any other base, but those are 4 reasonable options to do here. So regardless of which route you take, at the end, your decimal approximation should be the same no matter how you go, but your exact answer will look slightly different. So I'm just going to start here by doing just a basic a common log of both sides. So just plain old log base 10. So when you log both sides, this allows you to take the exponent and bring it down. That's a property of logs, right? So we can take these exponents, bring them down to the front. Make sure you put some parentheses around them. So we have 2x minus 3 coming down to the front in front of log of 4. And keep in mind, log of 4 is just a number. Okay, equals x minus 6, be sure to put that in parentheses, equals log of 9. Okay, so we're one step closer to having a solution because we've at least gotten the variables out of the exponent. Okay, so the next thing we're going to do is get these x's that we're trying to solve for out of their parentheses. So we are going to distribute this log of 4. Keep in mind that's just a number, and we're going to distribute this log of 9. Keep in mind that's also just a number. Okay, so we're going to have 2x log 4. So it's basically 2 times x times log of 4, whatever that number is. Okay, minus 3 log of 4 is all equal to x log 9. I tend to put my x on the front just so that I don't misinterpret that as being log of 9x. The x is totally independent of that log. Minus 6 log 9. I just noticed I put an equals here. That didn't need to be there. Okay, so keep in mind, your final goal is to solve for x. We've got an x here, and we've got an x here. So on the previous example, when we had to solve for x, it was a little bit prettier than this. We just had 4x minus 6 equals 3x minus 8, two linear expressions equal to each other. This is a lot uglier, but we're going to do the same routine. You're going to put the x's on one side, I don't care what side you put them on, and you're going to put the numbers, the constants on the other side. It won't really seem like that's what you're doing. They all look kind of crazy because all of these terms have logs in them, but some of them are just numbers and some of them, have x's in them. So I'm going to go ahead and bring this over here, group it with that x, and I'm going to bring this term over to this side to group it with the 6 log 9, which is also a constant. Okay, so right now I've got my x's grouped together and my constants grouped together. And notice, keep in mind, we're still trying to solve for x. So if I have x written twice and I just want to solve for x, I need to factor it out as a GCF. So if I pull out an x, that leaves me with 2 log of 4, keep in mind that's just a number, minus log of 9, also just a number, equals negative 6 log 9 plus 3 log 4. Okay, so we're on the home stretch here. All we have to do now is get x alone. So since x is multiplied by this 2 log 4 minus log 9, the last thing we have to do is divide by that. So we get negative 6 log 9 plus 3 log 4 divided by everything that was left when we pulled out a greatest common factor of x. So 2 log 4 minus log 9. And yes, this is an ugly answer, but that's our answer. And you can punch all this into a calculator to get a decimal approximation. So now I'm going to talk about an example where we have an exponential expression with e in it. And the funny thing about this one is how to deal with this e to the negative x that's here. All right, so the first thing we need to do, keep in mind we're trying to solve for x in the end. That's always our goal. And there's an x here and there's an x here. Okay, so the first thing we want to do is make this so that it's not a fraction. And the way we'll do that is multiply both sides by 2. As in, you can think of it as cross-multiplying, you can think of it as multiplying both sides by 2. Either way, you're getting that 2 out of the denominator and making this equal to 10 now. Okay, so at this point, kind of stop and take stock of what you have. You have e to the x plus 9e to the negative x. And now this is our funky issue to deal with at this point. So we don't really like this e to the negative x. So we will do what we know would undo that, thinking about exponent rules, which is multiply this term, by e to the x. And if we want to do that, we need to multiply everybody by e to the x, because we know that when we're solving equations, if we do one thing to one term, we have to do it to all the other terms. Okay, so we're going to distribute this e to the x now to every term. So e to the x times e to the x is e to the 2x. We've added those exponents because we're multiplying two terms that have the same base. Okay, plus, when we multiply 9e to the negative x, think about exponent rules. E to the x times e to the negative x, if you add those exponents, you get e to the 0. X minus x is 0. And what's e to the 0? Hopefully you're thinking, oh, that's 1. Okay, so if we've got 9 e to the 0, that's just 9 times 1, which is 9. Okay, all of this is equal to 10 e to the x. And some of you guys may have thought, I'm going to move that 10 over. That's fine. You could have moved that over to the other side. At this point, that's what I'm going to do anyway. So I'm going to get this all written on one side, and at the same time, I'm going to put it in standard form. So I'm going to subtract 10 e to the x, and I'm going to put it as my second term because that's the form that I want this to be in so that I can at least attempt to factor it. So you're going to factor this either by thinking about this as pretending that e to the x is just like x. So this is just like x squared minus 10x plus 9, which is obviously factorable. It factors into x minus 9 and x minus 1. And once you're done pretending, if you did that to kind of help you factor it, you have to keep in mind that that x is really an e to the x. So these are really e to the x's minus 9 and e to the x minus 1. Okay, so, and all of this is still set equal to 0, and that's why we factored, so that we could use zero product property. So we're going to take e to the x minus 9, set it equal to 0. That means we have to add 9 to the other side, so we get e to the x equals 9. And we have e to the x minus 1 equals 0, so we have e to the x equals 1. Okay. For this equation here, e to the x equals 9, the x right now is in the exponent, and you think to yourself, how do I get that x out of the exponent? Oh yeah, I log both sides. And here, because we have an e, it makes sense to do the natural log instead of log, because what's the natural log of e? 1. So we can just cross that out now, and we just have x equals the natural log of 9. So there's one of our answers. And we know that that's not extraneous because this was an exponential equation, and there's no such thing as extraneous solutions with those. Because the domain is all reals. So then we have this e to the x equals 1, and you have two options. You can either rewrite them with the same base, thinking about e to the x as just being e to the x and 1 as being e to the 0. So that's one way to think about it. I'll do that down here. E to the x equals e to the 0. Or you can do what we did for this one and just natural log both sides. If you natural log both sides, you'll get natural log of e to the x, which we know natural log of e cancels out, becomes 1, equals the natural log of 1. Okay, so natural log of e is gone, and we just have x equals the natural log of 1. Either way, regardless of if you do it this way or this way, we have a similar situation. The natural log of 1, you should know, is 0, because that means e to the what is 1. Here we have x equals 0, which is also the same outcome. So our final answer is not actually natural log of 1. Our final answer is x equals 0. Okay, so we got two answers. We got natural log of 9, which is a funny looking answer, but is still a number, and we got x equals 0. So hopefully this video has helped a little bit with different scenarios that you might see with solving exponential equations. Keep in mind that if you can rewrite with the same base, that's probably the easiest route to go. Keep in mind that taking the log of both sides undoes the fact that it's an exponential. You may want to do a common log. If you have bases of e, you probably want to do natural log because those cancel out. If you want to do common log, you can. If you want to do log base, one of the bases of the exponents, that can make it simplify a little bit better. It's just a matter of preference. Either way, your final answer, your decimal approximation, should make a true statement when you plug it into the original problem. So just keep that in mind. All right, I hope this video helped.